A beam of length 6 meter is simply supported at its ends and carries 2-point loads of 48 kilonewton and 40 kilonewton at a distance of 1 meter and 3 meter respectively from left support. That is, 48 kilonewton load is at a distance of 1 meter from the left support, whereas this 40 kilonewton load is acting at a distance of 3 meter from the left support. Okay, so the in between distance of 48 kilonewton load and 40 kilonewton load is 2 meter. Okay, so the question we want to find out is one deflection under each load. So what is the deflection under 48 kilonewton load, what is deflection under 40 kilonewton load, and what is the maximum deflection of this beam? That is second question. Third one, the point at which the maximum deflection occurs. So in which point the maximum deflection occurs? So these are the three questions asked. So the given E is 2 into 10 power 5 Newton per millimeter squared and I equal to 85 into 10 power 6 millimeter power 4. So this problem has to be done by Mech.Rajeswari method. Okay, so I said clearly in our class that the problem is having a simply supported beam, the central load only acting in the sense, then we can do it by double integration, whereas there have multiple loads offsetly acted on the beam, then the problem is tedious to get a solution. In this period we can use Mech.Rajeswari method to find out a solution. Okay, now simply supported beam is given and different loads which are acted on the beam. Then the first step is to find moment. Okay, before finding moment, so we can find out the reactions of simply supported beam, which is important. So taking moment about A, then the RB is acting anti-clockwise and this 48 kilonewton and 40 kilonewton is acting clockwise. Okay, now anti-clockwise equal to clockwise, anti-clockwise RB into 6 equal to clockwise 48 into 1 plus 40 into 3. So that is 168 kilonewton meter divided by this 6 meter. So then we can get RB equal to 168 by 6 equal to 28 kilonewton. So RB is 28. Now the total load which acted on the beam is 48 plus 40, that is 88. So 88 minus this 28. So reaction A is 60 kilonewton. So consider the section X in the last part of the beam. So we can put a section in between of load D and B. So at a distance X from the left support A. So that is at a distance of X from the left support A. So there have a section XX at a distance of X from the left support A. So the bending moment at this section is given by EI d squared y by dx squared, that is bending moment M, equal to in that section XS we have to find out the bending moment at section XX, which is at in between of that D and B there have an imaginary section. So we have to find out the moment at this section. So now this RA into X, moment RA into X, that is for that reaction load A. Then this 48, so moment from 48 kilonewton to, so that X distance. So you know that X distance is from section XX to left end. So for 48 kilonewton, that is X minus 1. So 48 into x minus 1, that is, see, this is reaction RA load is um, clockwise, then this 48 and 40 is anti-clockwise, so we put minus. So minus 48 into x minus 1, then minus 40 into x minus 3. Okay, so now RA value we know, that is 60 kilonewton, so 60x. For easiest understanding, we can put this lines. Okay, for each and every load we can put a line. So this is our equation. Now integrating the above equation, we can get, see, m equal to, m is ei d squared y by dx squared. We can integrate it, that is ei dy dx equal to, so that load 60x, so x power n equal to x power n plus 1 by n plus 1. So 60 x power 1 plus 1 x squared, 60 x squared by 2 plus this constant c1. So we can put this c1 in anywhere. So initially in first slab we can put. So next, minus 48 x minus 1 the whole squared by 2. Similarly minus 40 x minus 3 cube by 2. So this 48 definitely divided by 2. So 48 by 2 24, 40 by 2 20. Okay, that is 60 by 2 30. So this is the equation 1. So integrating the above equation again. So the first equation is slope equation. So second equation is deflection equation. Again we can integrate it. What happened? Ei dy by dx is integrated, then we can get y. So eiy equal to this 30x squared, 30x cube by 3 plus c1x plus c2, then minus 24x minus 1 cube by 3. Similarly on last slab, minus 20 x minus 3 the whole cube by 3. So that 30 always divided by 3, then 10x cube plus c1x plus c2. This is first slab. Second slab, 24 3, that is 8 minus 8 x minus 1 cube. Then 20 by 3 is not divisible, so we can keep as it is. So that is minus 20 by 3 x minus 3 the whole cube. So that is taken as deflection equation, considered as equation 2. Now we want to find out the constants C1 and C2. For that we can apply the boundary condition. So to find the value of C1 and C2, use two boundary conditions. The boundary conditions are at x equal to 0, y equal to 0. So at left end, x equal to 0, y also become 0. And then deflection when x equal to 6 meter. So the total distance is 6 meter. When x equal to 6 meter, then y at right end also become 0. So at left end x equal to 0, y equal to 0. At right end at x equal to 6 meter and y equal to 0. These are the two boundary conditions. So substituting the first boundary condition, that is x equal to 0 and y equal to 0 in equation 2, that is deflection equation. Then see, so deflection equation, left end means we can take that first slab only. So up to first dotted line we can consider. So what happened? Y, this y becomes 0, x equal to 0, y equal to 0, no, on that condition. So ei into y 0 equal to this x also 0, so 30 in the 10 into 0 cube plus c1 into x 0, that is also cancelled, 10x cube also cancelled. So c2 equal to 0. So that is the first boundary condition. Second boundary condition, substituting the second boundary condition, that is last slab. So we can fully write the equation, that is y equal to 0 when x equal to 6 meters. So 0 we can put instead of x 6. So 10 into 6 cube plus C1 into 6 plus C2 is 0. So minus 8x is 6. 6 minus 1 cube minus 20 by 3, 6 minus 3 cube. So we can simplify that is 210 equal to 10 into 6 cube 2160 plus this C1 into 6 6C1 minus 8 into 6 minus 1 5 cube, that is minus 8 into 5 cube, that is 1000, minus 20 by 3 into 3 cube, that is minus 180. Okay, so we can get numerals, that is 2160 minus 1000 minus 180, that is 980, plus this 6C1. This is the simplified form. Therefore C1 equal to minus 980 by 6, that is minus 163.3. So constant C1 is minus 163.3. Now substituting the values of C1 and C2 in equation 2, that is deflection equation, EIY equal to 10x cube minus that C1 is 163.33x and second slab minus 8 into x minus 1 cube, then minus 20 by 3 into x minus 3 the whole cube. So in this we want to find out the deflection y. So deflection under first load at point C. So at in this point C at 48 kilonewton place, that is deflection at C, y at C, and at 40 kilonewton, that is y at D. So now at the location of C at 48 kilonewton, what is deflection? So EI into YC equal to, so up to second slab, so 10 into 1 cube minus that 163.33 into 1. So up to this first slab, so this 10 in minus 163.3 equal to minus 153.33 kilonewton meter cube, because the load in kilonewton and the distance in meter. So we can get finally minus 153.33 into 10 power 3 into 10 power 9 Newton millimeter cube, that is meter cube kilonewton 110 power 3, then meter cube 2 millimeter cube 10 power 9. So totally we can have 10 power 12 while we converted from kilonewton meter cube to Newton millimeter cube. So now minus 153.33 into 10 power 12 Newton millimeter cube. So now you know the values of E and I, then we can get the deflection at location C, that is at the load of 48 kilonewton. Then we can substitute this E and I, we can get the load at that is the 48 kilonewton load, the deflection y equal to minus 9.019 mm. Negative sign shows that deflection is downwards. So the next one is deflection under section second load, that is at point E, that is at 40 kilonewton load position. For that means we can have first and second slab. So 10 into 3 cube minus this C1 163.3 into 3, that distance is 3, no, that is we can put x equal to 3. So minus 8 into 3 minus 1 cube. So we can get by solving kilonewton meter cube to Newton millimeter cube, we have minus 283.99 into 10 power 12 Newton millimeter cube. So that divided by E 2 into 10 power 5 and I 85 into 10 power 6, we can get the deflection at location D, or the deflection at 40 kilonewton load equal to minus 16.7 Newton mm. So the next we want to find out the maximum deflection. The deflection is likely to be maximum at a section between C and D. For maximum deflection, dy by dx should be 0, that is slope is 0. Hence equate the equation 1 equal to 0 up to second dotted line. So we clearly noted that the maximum deflection lies between the section C and D. So there have two slabs or two up to two dotted line we consider. So that is, we can take slope equation because at deflection only this dy by dx slope equal to 0. So that is 30x squared plus c1 minus 24x minus 1 the whole squared equal to 0. So you know the c1 value, that is 163.3. so 30x squared minus 163.3 minus 24, this x minus 1 the whole squared is x squared minus 2x plus 1. So we can simplify it, we can get an equation 6x squared plus 48x minus 187.33 equal to 0. So we can apply the quadratic equation formula, that is x equal to minus b plus or minus b squared minus 4ac by 2a. Applying this, we can get 2.87 meter. So the maximum deflection is x equal to 2.87 meter. Now substituting x equal to 2.87 meter in equation 3, that is equation 3 is the deflection equation. Okay. So EI Y max equal to 10 into that x is 2.87 cube minus C1 163.3 into that x is 2.87 minus 8 into x minus 1 2.87 minus 1 cube. So we can have minus 284.67 into 10 power 12 Newton millimeter cube. Then you know the value of E and I. Then Y max equal to minus 284.67 into 10 power 12 divided by 2 into 10 power 5 into 85 into 10 power 9 in power 6. Then we can get Y max equal to, that is deflection maximum equal to minus 16.745 mm.